captions. Yeah, so I think we'll start with a small presentation till like probably 20 minutes, and then we'll go with the tutorial. So hello everyone, my name is Daniil Boiko. I'm PhD student at Carnegie Mellon University in Gabriel Gam's group, and I would like to present this work on emergent autonomous scientific research capabilities of large language models. The work to a significant extent follows the preprint, which is posted in the chat. So there are three main technologies that could create trillion-dollar markets over the next decade. This include post-digital computing, precise gene engineering, and material science. Material science covers everything: drugs, some energy materials, just everything. And developing new materials is very expensive. It takes 10 years, $10 million to develop a new material. So it's really hard. And the main question is, how do we actually make molecules? The approach that we use follows this loop of designing what we want to do, going to the lab, making it, then testing for property we want to test it, and then performing analysis. And we can significantly speed up making and testing part. So we could use liquid handlers, we could use static platforms, we can go to the cloud lab and make experiments there. And CMU is opening the first academic cloud lab, probably like mid-September, where you can just write code that will be executed on these instruments, some of which are automated, some operations will be done by people. But two other parts of this loop is the design and analysis are really hard. And although there is quite a bit of work on AI or ML based design of like different materials and things like this, still not much work is done here. And what we try to do in this work, we wanted to go from prompts in natural language, pass it through some agent and get experiments performed in physical world. And for example, you could say synthesize compound A for me, or discover this drug, or perform this kind of experiments, and then the agent does all the work required to reach this goal. And we have the following architecture. So we have input prompt going here. We have the system which has the main module, planner module, which is just GPT-4 in chat completion mode, and it's connected to various tools, or if you use ChatGPT a lot, to plugins. And these tools include web search, and web searcher has access to Google Search API and can browse internet pages. Execution of the code, so planner can write code in Python that will be executed in Docker container. Documentation search for different experimental platforms, and finally automation. So planner can write code for either OpenTrans Liquid Handler or Emerald Cloud Lab. So web searcher is just a goal. So we have query of specific creation, and we'll just get an answer. Inside what we do, we make requests to Google Search API, collect pages, select pages to browse, and collect text from individual pages, and ask the planner to ask the GPT-4 model to compile the answer. And we want to test this thing, and for testing, we developed in a set of 7 compounds for which we knew that there is synthetic data accessible online. The prompt was something like provide synthesis for compound A, and the compound would be one of these compounds. So actually let's look at the data first. So first let's start with GPT 3.5. It's a purple bar everywhere. It usually gets like really bad synthesis. So, for example, absolutely wrong synthesis for ibuprofen, somewhat okay synthesis for aspirin, and the labels here. So 3 is just correct synthesis but not precise. 2 is synthesis that makes sense, but actually wrong. 1 is wrong synthesis, and 4 is correct synthesis with detailed description of all the steps, and 5 is like 4, but with all quantities and stoichiometry provided. So GPT 3.5 doesn't do a good job here. If you take GPT-4, it works significantly better, but there is some variance in predictions, and it still cannot do ibuprofen. If we switch to models where we have access to the internet, take this blue bar, which is GPT-4 with search capabilities as described before, we get excellent performance for 4 out of 7, and okay performance for ibuprofen, acetate, and nucleic acid. We can also observe individual predictions. So, for example, GPT 3.5 without search proposes, if you want to synthesize nitroaniline, it wants to do nitration of aniline, which is not a good idea because it will oxidize. Correct synthesis would include protecting NH2 group first. For ibuprofen, as you can see here, GPT-4 just provides some crazy solution, which absolutely doesn't make any sense. GPT-4 with search provides correct answer, but not detailed enough. That's why it gets score of 3. The next part is documentation search. And why do we need documentation search? For some platforms, information about how to use them is not available online. And for some of them, there is so much information that just Googling this information online will be not the best idea to access this information. And we developed 2 versions of the doc searcher module, which one of them has ability to navigate ECL documentation, and another one can access OT-true documentation, which is like open trans liquid handler. They're a little bit different in their architecture, but inside is just a vector database of indexed documentations for them, and then corresponding sections are aggregated, and we make predictions. And for example, if you want to do HPLC experiment, you say run an HPLC experiment, and you get correct code for running the experiment, which is constructed based on the data in the documentation. Finally, we would like to be able to perform experiments in physical world, and for that, what we started with is controlling open source liquid handler systems, and OpenTrans is very useful for that because it has ability to work with just Python code, and OpenAI's models write Python code really well. So if we just ask to develop a protocol for drawing a red cross, we'll easily do that. We could do more interesting geometric things like coloring every other row, drawing rectangles or blue diagonals. It can do all of that. We also can combine multiple hardware modules together. So, for example, this problem where we say that, okay, you have a plate. Plate has three valves with samples which are in unknown positions, and they have 3 different colors, yellow, blue, and red. And you need to design an experiment to identify colors in each of the valves. And what the model does first, it prepares sample, does it here, and then tries to do UVs on this plate. Then we manually transfer the plate, get NumPy, we get the data converted to NumPy array file and provide it to the model. And the model then writes code to analyze this UVs data to identify wavelengths with maximum absorbance, and based on these numbers, it correctly assigns samples to different wells. Finally, we got all these different modules, and we can connect also web search and do something even more complex. So here we try to perform Suzuki and Singashore reactions. We describe in the prompt, we describe the setup, saying that we have left pipette of this type, right pipette of this type, and what we have on the liquid handler deck. We also provide what compounds are in plate with source regions, and so they're grouped in the way that we have the first partner of coupling here, and for Suzuki you would need a true, for Snakashiro you would need a one, B1 to B4 to any of them, any of the catalyst, any of the bases. And once you run it, you'll actually see that first what it does, it searches conditions for the iterations, browses individual pages, and we use Selenium to browse these pages so we can bypass restrictions by publishers. Yeah, so it came up with the answer for conditions. And some descriptions, direction, general description. Now it identified compounds it needs to work with, and then knows that it needs to do some experimental procedure, but wants to start with calculating data for stoichiometry data. It writes code, but it doesn't use print statements, so Python returns nothing, then it tries to use it. But we run the script every time from scratch, so there are no variables defined before. Now it will write correct code to identify stoichiometry and to write code for the liquid handler. I think, yeah, so these are calculations and it goes with code next. So because it can make different selections, we can actually observe what the selections look like. And for Suzuki and Snakashiro, the first reagent, A1, which is phenylacetylene, and phenylboranic acid for Suzuki, phenylboranic acid for Suzuki, and phenylacetylene for Snakashiro, it makes correct selection in all cases. Then for Suzuki, it and Snakashiro, it selects iodobenzene in most of the cases, but sometimes sometimes it selects bromobenzene. For catalyst, there's more variety for Snakashiro. It selects more often NHC catalysts than phosphine-based catalyst, and DBU over triethylamine more often, but still with preference as before. And additionally, we can also compare which bases it selects for different catalysts. For example, we can see if it goes with NHT catalyst, it's more likely to choose DBU, and this preference inverts for Snakashiro case. We can also see, we can just ask to provide reasoning why these compounds are being selected. And for example, for Snakashiro, it could select nitroiodobenzene, saying that iodine is a better leaving group in this molecule, which is right. And for B2, which is bromobenzene, in Suzuki, it selects it for higher selectivity. And also we can browse individual pages and see, like, the model can browse individual pages, and we can see what pages it browses. And top 5 is Wikipedia, chem.libertech.org, organicchemistry.org, and ACS and REC websites. So pretty good selection of pages to visit. Once we got the code for the liquid handler, we actually perform it in the lab. And of course, it's not like very high yield, but these are the first reactions performed end-to-end by LLM. And you can see a bit here which corresponds to diphenyl for Suzuki reaction and diphenylacetylene for Snakashiro. So what we can do, we can go from prompt in English to chemical synthesis. So it's very nice. We can do experiments in the cloud lab, for example, to perform HPLC experiment. And this was one of the last experiments performed in the South San Francisco side of ECL before they moved to Austin. And they were packing, and HPLC experiment went a little bit wrong, but the command and the code correct. So we can go from English prompt to fully realized scientific experiments. But when we think about science, science is not only running reactions in the lab or performing some experiments, it's also the ability to reuse and aggregate already collected knowledge. And we designed additional tests to see if these models can actually do that. We started with this data set from science paper where for a certain set of ligands, bases, and solvents, entire space of conditions is covered. So all possible combinations of them for a specific pair of substrates. And we developed a game. So the game looks like this. You says that like you have these two substrates. And in every step, you have to guess ligand, base, and solvent that if you would run this reaction in the lab, you would get the highest possible yield. And each time you make this guess and you get answer back with yield for this specific set of conditions, and then you make another guess. And over time, you're supposed to make better predictions. We evaluate performance and what you'll see on the plots below by using normalized advantage. This is yield at the current step minus average yield for the specific pair of substrates divided by difference between maximum yield and average yield. Why is this formula? So if you have absolutely random behavior, every time you select your conditions randomly, you would get average yield here. So this normalized advantage would be 0. If you made the best possible selected the best possible conditions, then you get maximum yield here, and normalized advantage should be 1. So it allows us to compare cases for different substrates where you may have the best condition for a specific pair of substrate, like 10% yield of 10%. So we can align all these values using this metric. So GPT 3.5 it doesn't work well. You'll see in comparisons that's not much points here because it just doesn't follow instructions well. But when we go to GPT-4, we have two cases with GPT-4. We see actually pretty good results. So on the left, you see GPT-4 with prior information. It's the 10 data points for different substrates. It's just different substrates, different conditions, and just yields for them that could help the model. And on the right, you see GPT-4 with prior information. Two bottom plots are normalized advantage values. And as we can see here, they increase over time. And what it means that each attempt, you make a better guess of conditions. So you manage to reuse already collected data to make better guesses. And we also analyze normalized maximum advantage, which is just maximum normalized advantage till current step. So it just shows how well you're doing overall. You may guess the best conditions right at the start, and then there will be other guesses will be bad, but your initial guess was good. So you basically solve the problem. So that's why we use normalized maximum advantage. And we can see that it starts with greater values than case without prior information. So it's good, but it converges pretty much to the same value. The value is pretty high, is around 0.85 of maximum yield, but actually like difference of maximum average yield plus average yield. We did the same thing for another data set from paper from Doyle group on bulk heart regression, and there are varied ligands, additives, and bases. And here we compare two approaches to represent this the structures. First one is just compound names, and the second one is small strings. And we see very similar performance in both cases. But interestingly, if we just analyze individual runs, we can see that, for example, here, what the model says that like yield improved. Let's try the first ligand again and change the additive, and changes the additive to this additive. Then it gets the yield back, which is 41%. And then it says, okay, let's try another additive that has stronger electron withdrawing group to further increase the yield. And if you just look at the structure, it indeed has stronger electronic withdrawing group than phenyl group here, and yield decreases. So it has some basic understanding of chemistry. Yeah, it's some extent. But when we develop things like this, we significantly lower barrier for entry for everyone. I mean, now you don't need to know how to use different instruments. You don't really need to know chemistry. You can just say synthesize this compound, and there is some potential for misuse of these systems. And we designed a set of I think it's like around 40 different compounds from Schedule 1 and 2 drugs by DEA and chemical weapon agents. And if you look at the representation as a compound name, so you could say synthesized heroin, for Schedule 1 and chemical weapon agents, mostly it refuses immediately. Or it may do some search online, but without even providing synthesis information, we will just say no. But if you go to more complex representations like smile strings or UPAC names, pretty often it just goes all the way to writing an experiment command. So our understanding is that there should be some security level that transforms all chemicals mentioned in prompts to some unified representations that can be compared against databases to prevent misuse of the systems. And we have a web app to control the system. So right now we don't release access to the papers under review. We don't release access to the web app, but it may or may not happen in the future. It just depends overall on our ability and ability of any regulators to control misuse part of the system. So what we did here, we developed intelligent systems that can autonomously design, plan, and perform complex scientific experiments. We have shown that there is a potential for misuse of these technologies, and we're developing guardrails, but overall, like help from the community. There should be more community involvement in this area, in our opinion. And this work was supported by various organizations, and I would like also acknowledge co-authors of the manuscript, Robert McKnight and Gabe Gomez. And thank you. I think we could just, if there are any questions, we could, on presentation part, we could discuss now and then go to hands-on section. So.
Yeah, this is good. Thank you. Very interesting. Yeah, I have doubts of, with respect that if those, do you think that OpenAI took, don't know, the papers that you tested as part of the data set, right? So we don't know exactly what is in the corpus they used to create the model. So probably it's not just
Yep.
probably some parts are hard coded, right?
Yeah, it's a good question. I think the best case to see that it's not that this example. So when we compare online search and once we go to more complex cases like ibuprofen, original models fail. So we can make such comparisons, comparing case of the model without access to any tools and model with having this access. And we see once we go to something more complex, original GPT-4 models fail. If we want to like go to part of writing protocols for OpenTrons, GPT-4 originally does it pretty well, but because it was trained on the data till like 2022, it doesn't cover all hardware released after that. And after that, OpenTrons had released heater shaker module, and GPT-4 will write wrong code for heater shaker module because they just changed methods names a little bit, so it doesn't work. But once we have documentation tool, it can actually see that it got it wrong, go to documentation, see how to actually write code for heater shaker module and change it. So it's all about comparing with having access tools or not, and we can evaluate these differences. But yeah, it's a good question. Thanks.
Okay. If there are not more questions, I think we can move on to the hands-on part. I put the link in the. I will put the link in the chat. There's a question from Esther. She's in Vienna. She's asking how much do you think we can or we should protect such systems against misuse? And the second question is how do you go about this problem in, for example, project applications?
Yeah, so I think we should protect it against misuse. One of the cases where it actually can be really dangerous is the case of Cloud Labs. So in Cloud Labs, average Cloud Lab is a place where you have like all this hardware, but you still have people there that move samples between instruments. Mm. All these people actually worked on Amazon warehouses, for example. They're not qualified, and they got like 2 weeks of training. They don't know chemistry. They don't know what they're working with. And if you as a chemist can identify threads in what you do in the lab, you can say, oh, I shouldn't mix that. These people cannot do that. And in the Cloud Labs, these people are actually like the most vulnerable. And you could imagine trying to perform terrorist attacks on Cloud Labs. So this can happen. And if before it required some knowledge from you, so just some expertise, now you can just if guardrails don't work well enough, you could write synthesize mustard gas, and then it would just make this and write the code for synthesis. You just copy paste and run it in the real Cloud app. So there is some potential of misuse, and potentially it can be really dangerous. About the second part, does the second part is about misuse as well, or just general application? It's not about misuse. I mean, if we have our own project where we want to test it, then misuse is not a problem because only we have access to this thing. And the same way as now, like at least before paper is published, only we and the reviewers have access to the tool. But not for this, just because we don't release it. But one of the reviewers for the paper strongly advised against releasing this publicly before there is some public policy on AI in general and these risks. And apparently is being developed and discussed, but yeah, thanks.
Yeah, there is a fine line between regulation and innovation. So I guess you don't want to, so you want to be innovative, but also you don't want to over-regulate.
Yep.
And yeah, there should be a equilibrium between the two. And yeah, probably we need committees for ethics, but smart enough to know to stop innovation. So okay, I think this is the answers were. I mean, you gave the answers for the questions. I guess we can. So let's move to the collab. I don't know if we need a OpenAI API key, but if we do, let's imagine that we have it. If not, yeah.
Actually, let's.
Yeah. I let you to explain. Okay.
Yeah, let's. I know. Let's do what I'll just post this key in the chat, and I'll just revoke it straight after. Oh, wait, actually, I will just make a new one. But yeah, if you have your own account, you can just follow the steps. So. So yeah, there is a link in the chat for collab. I can just paste it again, and there is a key. So yeah, what we'll try to do here, we'll try to use OpenAI API, and we will discuss what things in chemistry and chemical applications can be used, but without doing any chemistry directly. And we will build also like very small, easy autonomous agent to guess numbers. So it will be very fun. The first what we do, we install OpenAI Python client. So we installed it. Wait, we just enter API key. So just normal completion mode has been is now legacy and still maintained, but apparently for not for long. And the best approach is to interact with this model is chat completion mode, and it's the same things that you would see in OpenAI API. In ChatGPT, and you can do this with OpenAI API. So when you use chat completion mode, you interact using messages, and each message has a role, and role is one of system, user, and assistant. So system is just defines how chatbot is supposed to act. User just messages from user, and assistant messages are from assistant. And everything generated is supposed to be assistant, but not necessarily. And you have content with just a message. And here you can say that you're a very helpful assistant as a system prompt. You can actually also test it in Playground. So here you can do the same thing. You can select models, but we will do it here. For example, user goes to ChatGPT and says, "Tell me about Carnegie Mellon University." And you can generate completion by calling OpenAI chat completion create. You put your model, set of messages, and API key. It can also provide multiple options, so you can go to choices. We select the first one here, but you can ask for more and select the message. So let's do that, and it may be a little bit slow, but we'll wait. If you wanted to make like any work with OpenAI API yourself, this is the best work. This is the best way to work with it. Many papers now, not many, but there are some papers that people just copy pasted things from ChatGPT interface, but this is not really reproducible. Here, if you fix the model for specific date, like this one, then and lower temperature, then it will be reproducible. So yeah, we got the answer. So Carnegie Mellon is a private global research university located in Pittsburgh, and there is a nice description of Simbi. Actually there are plenty of parameters you can put in there, but I would say there are two very important. The first one is a model, so you can get current GPT-4. You can take GPT-4, which one, like the first version when it was released, and you can take GPT 3.5. And here we just generate completions for all three cases. And you see, we also use GPT-4 model here, but we don't get the same output. And this happens because all next tokens, they're sampled. And this is controlled by temperature parameter, and it's set to default of 1. So this is older GPT-4 model. It provides like quite a different output than GPT 3.5. So overall, they actually pretty similar if you just read them. And I was saying about temperature. So it selects based on probabilities of next tokens, but you can use temperature to alter this distribution. And if you set temperature to 0, you just select next token with highest probability. And if you run it multiple times with temperature 0, it will be providing same outputs every time, but not for other temperature values. So it's still very similar, but once you go to true, it like till the end just like goes crazy, and it just doesn't work well. Good temperatures are around 0.7. 1 is actually fine as well. So and just empirically affects creativity a lot. So if you go with 0, it's just not very interesting. The next important thing that actually got like released recently is function calling API. So imagine like in the presentation we discussed that there are various tools. We use different implementation of how it works, but now you can use function calling. And if you have set of functions, like if you have functions for multiplying numbers, you could define the description of the function. It has function name, description, parameters of this function that include, in our case, number 1 and number 2 of type number, and you can have descriptions for these properties. And then you can set required parameters. So you are doing the same thing. You say that like, okay, system prompt is just your very helpful assistant, and user says multiply pi by e. And in completion, you can create completion with GPT 3.5 Turbo, and you also provide functions. And what it returns, instead of just message, it returns function call that calls function called multiply with the following arguments. Sure, pi and e, which is correct. And then you can extract these arguments and get the output. So function calling is a very convenient thing, and it works really well. So next, actually, are there any questions on this part? Because it will get more complex. Yeah. Apparently no. Yeah.
No, so there's the only comment. So in this function, you are not explicitly saying 2 times, right? So you don't give them the formula, correct?
Oh no, yeah.
So this is the interesting part, right? So it's guessing so it understands what means multiply, which is, I mean, you can do this more complicated, but, right? But so multiplication is very simple, right? But you can give a very complex function, and probably just the system will understand what is the function inside. I mean,
yeah, it's right. So, like for example, for the system we discussed, you could imagine having a function called Google. This would get query, and then you do all required work here to get pages. Then you get like select page based on something, and then you generate output. Another function to generate output based on the page. So you could make other functions to execute code. You make OpenAI provides their favorite example of weather, so you could have a function that gets weather for a certain location, and this all could be just separate functions, and you would describe them here. Yeah, so the function call provides arguments, and you can use them to make it. So here, let's just try to see how we can build something autonomous. And the idea of autonomy is that we don't provide user input every time. So normally, if you use ChatGPT, you got the answer, and then you say, change this answer or do something else, or aggregate data in some way, but you're always in the loop and trying to interact with the model. And here we want to make it like fully autonomous without any involvement. So we generated random number, and this is just what we guessed. So we guessed 3. And we have the following messages. The first message is system message saying, you must guess user's number by iteratively making guesses. You cannot write anything else, only a number. And user says, guess my number. Okay. And what do? We have a loop. We have 50 iterations. There are 50 numbers, so we have 50 iterations. And at every step, we make completion from messages. So if you're doing for the first time, it will just make a guess. And it cannot write anything else, only a number. So yeah, just a number. To make the choices, and we select the number from the completion. Once it did it, for every new run, we have to provide messages again. So that's why we add new message generated by the assistant into these messages. So we do messages append here. Now there may be a case when it didn't follow the format that was described here. And with models like GPT 3.5, it happens quite a lot. So we try to extract the number from completion, but if it fails, then we just say you haven't followed the specified format, provide only a number. And again, it just goes as another message in messages. Finally, if number is our number, it's great. We just print it one and break. If not, then we append another message saying that like it's wrong, try again. So it made guesses, still makes guesses, and it's not very lucky with the numbers. And it guessed number 3, and it did fully autonomously. We didn't have any involvement here, so it's great. And now we can use it to guess our numbers, which is very useful. But it just like there is no decision making involved. I mean, you just like the only thing model has to do is just every time guess number it haven't tried before. It's the only decision making it has to make. But let's first try to make it to reason about what's doing. So in the presentation, there was example for guessing different ligand bases and solvents, and you can do very similar thing here. So you must guess user's number, and we force it to use JSON format of the following structure, and it cannot write anything else, just this JSON. And user says guess a number between 0 and 50 again. And if you do that, it follows the format, says it will start guessing numbers, guessed. Since 25 was incorrect, I will try lower. And it doesn't make sense to do any reasoning here, but I mean, it tries. So I'll try higher. Yeah, so yeah, I said only to 5, so it's not very interesting here. I mean, it's now we have reasoning and it says that it was incorrect. But let's do even more complex behavior. So let's say that, okay, you provide us a number, and then we compare this number with what we guessed. And if the model is smart enough, it can actually use something like by just splitting into 2 parts entire range, just some like binary search and just getting to the correct number. And let's see if the model actually can do that. So again, you must guess number. You'll get JSON format. You cannot write anything else. User will compare your guess with their number. And again, we're saying guess number between 0 and 50. And here, the only difference here that we have, we say that it haven't followed the format as before. It won't, yeah, everything's the same. But here we say that instead of it's wrong, try again, we say my number is greater or less than your guess. And let's see what it does. I'll start with a middle number. It's a very smart decision. If you can compare numbers, if you get these comparisons, since your number is less than 25, I will try middle range of 0 and 24. Yeah, and it just got to the number. So it selected the most optimal way to do this guessing part. Just by splitting the range into different parts. And yeah, so we have this autonomy, and now if you have a problem like this, you can actually make it do autonomous things. The only thing that you would need to build, something that was described in the presentation, is to enable function calling in there, as described before. So you could imagine in this loop getting completion, and then trying to see if there was a function call, and then if there was a function call corresponding tool, append output of this tool to the message list, and then try again. And doing so, it's possible to do really complex autonomous tasks that require calling different functions. So yeah, that's it on the hands-on part. Are there any questions? Yeah, it went faster than I expected, but yeah.
No, that's good. Thank you. So how you do? So I wonder if you do differently when you are speaking with the system in terms of chemistry. So do you give a role or something like that?
Yeah. So if you want to control it, actually, yeah, 1 second. In our work, what we had to do, and actually let's try. So it already knows quite a bit of chemistry. It doesn't know all the chemistry. That's why we have to rely a lot on different tools. But you still can say that like you're a very helpful assistant for chemists. And in our case, we had to parse all outputs manually and force it to use a specific format for calling tools. But you can say that like you have access to the calling tools. And it will be different from it, but let's compute, so we'll do it. So something like this. The model has access to 3 different tools, and we can say develop a more soluble version of probably no also answering probably profit, but let's see. So we got these messages, and let's just see what it generates. You would need more than this. So I mean, it's just as an example, but it's quite hard to make it follow very specific format. It's way easier with the first version of GPT-4.
Okay.
But once, yeah.
I'm not sure, but it seems like the API for GPT-4 is not is restricted, right? So you need like
I think, yeah, I think it got publicly released.
Okay.
So let's take this one. So let's determine scalability, and we can okay, there is no command provided. So let's just, what we'll do here a very simple thing. We take these messages, and in the loop you would just append another. You would just provide append as output as we discussed like below in the autonomous agent part. So this is output of the agent, and then what we'll say is that actually you haven't provided any command. We got these messages. Let's yeah, so I apologize for oversight. Let's determine the scalability of ibuprofen with scalability tool. And this is what it did. It tried to determine scalability of ibuprofen. When you want to build the system to work like really well, you have to do a lot of prompt engineering here. For example, it guessed smile string for ibuprofen, and it looks wrong, but or maybe it's not. But what you would probably would like, you in the system prompt, you would like to use tools all the time without trying to use its own chemistry knowledge, because it probably will be wrong. So there is lots of prompt engineering going in there. We just like have like around a page long prompt for our system covering all situations like this. So it just like gets reliable enough for if you have any initial questions about the work, feel free to email if you just like don't want